All right, so for today's lecture, I'm going to talk about the solution of time-dependent elasticity problems, and actually I'm not going to talk about material behavior that is time-dependent, but just the fact that there's inertia in the system. So I'll talk about the time-dependent material behavior like viscoelasticity or plasticity for the next lecture. But for this one, just give you a little bit of an idea of what happens when in your weak form you have this extra mass times acceleration term. So the weak form of the linear momentum balance for time-dependent problems has the same internal forces, so you still have to calculate the same internal residual, this stress double contracted with the variation of the symmetric velocity gradient. That's exactly the same as before. The external forces also the same as before, the integral over the boundary of the tractions times the variation of the displacements. And the thing that is different now is that instead of the sum of the external forces minus internal forces equals 0, here it's equal to the inertia, which is mass times acceleration, where or mass times v dot. And so that means now that there's not just the displacements as of known, but the displacements, velocities, and accelerations. So also typically you don't only have the inertia equals the displacements, but you end up adding some damping, and this is probably, if you remember your dynamics classes, where you have typically the equation of motion of a system has not just springs, but has some dampers in there. And then you don't get these perpetual oscillations, but the oscillations will die down because of some damping. And in the general form, you can write the equations of motion for the elasticity problem as mass times a vector. Again, this mass is a mass matrix, which is you can I didn't put it in this slide, so I can put an extra note on what this mass matrix looks like. But it's basically just the integral of the density times the shape functions, a pair of shape functions. So the combination of shape functions ij for a given element. And the u double dot here is a vector of all the nodal accelerations. And this damping usually is either proportional to the mass or sometimes proportional to the mass and the stiffness. Typically it's added and it's relatively small, and it's just used for damping down oscillations, so you don't have oscillations that go on forever. And then this is the same internal residual. So this is basically the integral of sigma double dotted with delta d, your standard residual. And then this matrix, this damping is a constant matrix, and this mass matrix is also a constant matrix. And as I said, it's just the integral. The reason why, if you remember the way we calculate the residual, we cannot take the u outside because there's some nonlinear function. The stress is a nonlinear function of the displacements, but the inertia term is a linear term, right? So the inertia term is just if you think of the weak form, you will have the integral of the density times the acceleration. So when you do the weak form with that, the acceleration appears linearly, so that means that you can take it out of the integral. So the thing that ends up in the mass matrix, for example, is just the integral of the density times shape functions. That's all you end up with in the mass matrix. And so you have to solve this now. And as I said, now the unknowns is not just the displacement, but now you have this thing that changes in time because you have displacements, velocities, and accelerations. So you can see this as a system of ordinary differential equations where you have u dot equals v and v dot equals you can rearrange this a little bit, and you can get v dot equals some function of v and u. And there's ways to integrate this system of ordinary differential equations, and you have probably done something like this in the past, where you can use different discretization schemes to move this over in time. So again, like you can see now, you have some unknown the displacements and velocities. So not just the displacements as of knowns, but displacements and velocities. And you have an a system of ordinary differential equations that you need to integrate. So how do you do that? Well, you need to discretize in time. And typically some finite difference scheme is introduced. So the v of t is the derivative of the displacements, and it usually is approximated with some finite difference scheme, like I said, with some weights for the displacement at the previous time step, the displacement at the current time step, the displacement at the next time step. And then, so once you introduce this type of discretization, you have to do something similar for the acceleration. Then you can think of having the unknowns are the acceleration, velocities, and displacements at the next time step. So a n plus 1, and just for sake of notation, n plus 1 denotes the next time step, n denotes the current time step or previous time step. So basically, you assume that you've already computed and you know the acceleration, velocity, and displacement at the time step n. Those are known. And then the unknowns are acceleration, velocity, and displacement at the next time step. And they have to satisfy this linear momentum balance equation. There's two choices. There is, depending on which, so basically all boils down to what type of discretization you use. There's explicit time integration, in which all the nonlinear terms of the equation of motion depend on quantities from the previous time step. So they depend only on an, vn, and un. Both the internal forces and the external forces, they're still nonlinear, but they depend only on things that you already know. So you only need to be able to compute the residual and not the tangent. So there's no need to do Newton-Raphson iterations. The disadvantage of this method is that, or this type of methods, is that they are conditionally stable, meaning that depending on your choice of time step, solution might blow up. So you have to be careful with that. Typically used for things that have shocks or some high frequency solutions, because in that case, either way, you have to take a small time step. So then might as well just do it cheap, because this doesn't require the solution of a linear system of equations. Then there's implicit time integration, where based on the discretization, the internal forces depend on the unknown displacements un plus 1. And so that means that because the internal forces are nonlinear and they depend on the unknown, then you have the nonlinear system of equations that you need to solve with Newton-Raphson. Now, the advantage of these implicit methods is that, okay, now you need to compute the residual and the tangent, but the time steps can be very large. Now, the downside of this is, of course, if you take large time steps, you might lose some accuracy. So like I said before, if you need to capture some high frequency solutions, then you have to take small time steps anyway. So then there's not really that much advantage for the implicit time integration. But if you are computing some solution where there is no shock waves or things like that require a small time step, then you can use this type of scheme, because you can take large time steps. So for the explicit time integration, consider this discretization where the velocity is a central difference scheme and the acceleration is also a central difference scheme, second order, with respect to displacements. If you plug this into the equation of the weak form, what you end up with is the equation of linear momentum balance, where the only unknown is the displacement un plus 1. So it looks a bit more complicated than before, because you are plugging in these two things into basically this equation. But after you rearrange, basically all you need to compute is this displacement un plus 1. So the mass matrix plus some time step over 2 times the damping, and then the unknown displacement. And then you can see that everything on the right hand side, So you only need the forces at the previous time step, you only need the internal forces from the previous time step. So R depends only on UN, so only on the known displacements U at time step n, and then here you need the displacement at the like n-1 time step. So you can see that here basically all the things that you have are the displacements at the previous two time steps. That's all you need, and then you can solve for the displacement at the next time step. In order to initialize this, you need to approximate, well, solve for the accelerations from the time zero that satisfy the linear momentum balance, and with that you can approximate this u minus 1. That's about it. So basically you are given u0 v0. With u0 v0, compute a0, compute u minus 1, and that's all you need, because now you have u0 and u minus 1 and v0 and a0. So you can compute vn, an. You can use that and plug everything here, but actually it's only in terms of un and un minus 1. Compute un plus 1, right? So that's the next time step. And then that's it. You're done, right? So you have the next displacement. You can update your velocity with that. So now you have the vn plus 1 is gonna be with your new displacement, and so this basically all will be plus 1, and then continue, like basically this has to be a loop in which you compute for this un plus 1 in a loop. And there's no need, so there's kind of a need to solve a linear system, because you need to invert this matrix, but actually these matrices are constant, so you only need to invert them once. And there's some ways in which you don't even need to invert them. If you compute the mass matrix in some special form, which is called diagonalization of the mass matrix, then you don't even need to compute the inverse. An alternative is to express in terms of the unknowns acceleration at time n plus 1. So that's just, again, explicit time scheme. This is the time discretization. And then if you plug that into the linear momentum balance, then you get this. So here, again, note that you have to evaluate the residual not at un, but at the approximated un plus 1. But still depends only on quantities at the n time step. So given that you know the displacement at time step n, the velocity and the acceleration, you can compute, this is the approximation of un plus 1, and use that to compute the residual. You have your forces, you have some damping, and then here it looks like before, but the only unknown is the acceleration. So in this case you would compute for the acceleration at time n plus 1, and based on that you can update your velocity and your displacements, and then repeat. So compute the next acceleration, update velocity and displacements. And you need to, as before, you need to have the initial conditions, so velocity and acceleration, and you can compute the initial, velocity and displacements, and you can compute the initial acceleration from the linear momentum balance. As I said, the thing with the time, the explicit problems is that the time step is, you have to pick a time step for the thing to be stable, for the algorithm to be stable. And typically the time step has to be equal or less than this ratio, which is the mesh size over the speed of a compressive wave in a linear elastic solid. So approximately, because obviously this is not a linear elastic solid, so this is not exactly true. But it's a good approximation for what the stable time step is, where this is the bulk modulus, the Poisson ratio, and the density. For implicit time integration schemes, the most popular one is the Newmark method family, which is defined in terms of this alpha, beta, and gamma. So beta here, gamma here. I guess there's no alpha, just beta and gamma. And uh, depending on your choice on beta and gamma, you get different schemes, and this comma is wrong. So if you plug this into the linear momentum balance, you end up with this equation, where it has been rearranged a little bit. But if this gets plugged into the linear momentum balance, then you get some term that multiplies the unknown accelerations, then the internal forces, and note that the internal forces depend on un plus 1, which depends on things that are known, but also things that are unknown, namely the acceleration. So it depends on if you plug this into the residual, so you want to evaluate your internal forces with the new displacement. You can see that the new displacement depends on displacements that you know, velocities that you know, accelerations that you know, but accelerations that you don't know. So there's one unknown here, this an plus 1. And the problem is that these are, the internal forces are nonlinear. So this is where you see that this leads to some nonlinear system of equations for the acceleration at time n plus 1. And then whatever is, when you plug this into the linear momentum balance, whatever depends only on un, vn, and an, you can put it on the right hand side. It's not derived in the book, but really it's not that bad. So basically, if you plug these two into this part, and then basically just move everything that has a linear dependence on un, vn, and an to the right hand side. And then the only thing that is left on the left hand side is the thing that multiplies the unknown acceleration, and the residual, which, as I said, is the internal forces associated with displacement un plus 1, which depends on mostly known quantities, but because it depends on this acceleration, then this introduces the nonlinear system of equations. So you need to solve this. How do you solve this? Usual Newton-Raphson scheme, solve for the accelerations. Depending on the parameters of the numeric method, one can recover the explicit scheme. For example, if you pick gamma equals 0, then you actually recover an explicit scheme. Otherwise, the optimal one would be gamma 0.5, and then you can see that there's no error in the amplitude when the damping is 0. There's a small error, so order delta t square, and then for stability you have to pick beta greater than 1/4, greater or equal than 1/4. So these are just different choices for gamma. And then an alternative formulation is, if you want to, just for going back here, in this formulation the unknown is the acceleration at time n plus 1. You can reformulate things so that the unknown is the displacement. And so you can express the acceleration and the velocity in terms of the displacements at un plus 1. It's the same method. Beta and gamma appear here as well. But when you plug this into the linear momentum balance weak form, then you get a system of equations where everything gets expressed in terms of the unknowns un plus 1. So that's the difference, basically. It's still nonlinear system of equations, so you can see that residual at time u depends on the displacements un plus 1, which are unknown. So here you can see this is basically like what we had before for the time independent problems. You have an internal force that depends on the unknown displacements, and then for the mass and the damping, they multiply things that are with respect to the known displacement, velocity, and acceleration, but also the unknown displacements. So you have to solve this system of equations for un plus 1. Again, you do that with Newton-Raphson. So this will be for every time step you need to solve a system of equations with Newton-Raphson. So you get two loops, a time loop and then a Newton-Raphson loop inside. And I think that's all I have. Yes. So these are the basic recipes for time integration, and this is chapter 6 of the Riggers book. For those of you who are doing any sort of time dependent problem. And then the one that I'll talk about on Thursday is going to be where material has some time dependency, so like plasticity, for example, or viscoelasticity. We have some rate equation for the constitutive model. All right. Well, see you later.